Okay. Hi, folks. I'm Sushain, tech lead for Stripe's Build Infrastructure team. Stripe minted its first remote Basil service back in 2018. We've been investing in our homegrown services since then. I'm excited to share how we've tackled some of the most interesting challenges that we've encountered along the way. So let's kick off with a quick recap of Basil remote caching and execution, just to get everyone on the same page. This will be a bit remedial for some of you, so just bear with me a little bit. So remote caching allows the Basil client to avoid redoing work that's already been done. Yeah, we all know that. It communicates over HTTP or gRPC with the remote cache endpoint that provides two gRPC services, the Action Cache service and the Content Addressable Storage service. The Action Cache service lets Basil store and retrieve cached actions. Right? The Content Addressable Storage service, also known as the CAS, lets Basil store blobs indexed by their checksum. Right? Stripe's Action Cache stores results in DynamoDB, and our Content Addressable Storage stores blobs in S3 or DynamoDB, depending on how big they are. So remote execution, on the other hand, allows the Basil client to distribute build and test actions across multiple computers. Aside from the standard performance and efficiency things we get about from that, it also avoids the classic, yeah, that works on my laptop, doesn't work on your laptop problem, because actions are executed on this standardized environment that users can't directly control or impact. Basil can communicate with the remote executor gRPC endpoint using the execute RPC. Under the hood, our remote executor endpoint is a scheduler that load balances across an underlying fleet of workers. That's not super uncommon. So with that background out of the way, everyone's on the same page. Let's talk a little bit about Basil infra at Stripe. Our Basil remote infra is responsible for running tests and builds for Ruby, Java, TypeScript, Go, and half a dozen other languages. You name it, we're probably building it with Basil at Stripe. So everyone hates waiting on builds. For example, our TypeScript devs, they're used to their blazing fast native tooling that's powered by some bespoke incrementality baked into it. We execute 80 million actions remotely every week. Making them as fast as we can is crucial to providing a delightful user experience for everyone. Even our service infra relies on Basil through remotely executed Terraform builds. Keeping our builds reliable, regardless of external downtime, is critical for us. Even if Oregon were to sink into the Pacific, we want our builds up, right? So every calendar year, our remote actions execute for over 100 years in aggregate, and our users expect minimal disruption throughout this process. Go services underpin our security. Even a single poisonous instance across the 65,000 vCPUs that run remote actions could allow an attack against our in-house certificate authority. So a secure foundation for our builds is just non-negotiable for us. So we've got three major goals that I've laid out: performance, reliability, security. So for the rest of our time together, I'll take you on a bit of a whirlwind tour through some of our more novel approaches to challenges in each of these spaces. So we'll kick this off with security. Remotely executed Basil actions, they have to run somewhere, right? So to amortize the startup costs and the overhead of supervising all these actions, we reuse trusted workers across multiple actions. A single worker can run dozens of actions at a time concurrently, and hundreds of thousands of actions during its lifetime until it gets shut down and recycled. Sandboxes are how remote execution systems manage all of this stuff. So each action executes in its own sandbox. Their key mechanism for assuring actions are isolated from a security perspective, but they also have a bunch of user-facing benefits, like Kubernetes deployments that you might be familiar with. They also have resource and file system isolation. It means that actions just don't have to worry about noisy neighbors and the problems that those cause. So until late 2020, our execution service relied on gvisor, Google's user space container sandbox. But as we brought more languages into the Basil fold, like that slide before, gvisor just couldn't keep up with what we wanted. For example, running a single Ruby unit test that immediately succeeds, didn't do anything, took 6 seconds under Docker, and 10x longer in gvisor. We narrowed down this issue to gvisor's file system overhead. Languages like Ruby and Java, they resolve imports by linearly scanning through a load path or a class path. In that Ruby test file, we observed over 600,000 file system syscalls, searching a load path over 500 directories in that 6 seconds or that 60 seconds. So the file system overhead emulation, it led us to gvisor. Sorry, led us towards Firecracker. Firecracker's micro-VM approach improved our security posture by further reducing the attack surface just to the Linux KVM, and it solved our problem with close to native file system performance. As you heard earlier just now, it also gives some other really powerful capabilities to the table. So that's that one. One of the benefits of Sandbox is improved hermeticity control, right? So we don't want actions making arbitrary requests to the internet. It harms their reproducibility, it harms their determinism, and it provides a vector for all the supply chain attacks that we're all scared of. But it turns out, like, in life, we just can't always avoid the internet. It's pretty sad. For example, we have these integration tests, right? They want to use browser stack to render our front ends on a bunch of devices. The prospect of maintaining a bunch of iOS devices is just not very exciting to us. So these tests need access to these browser stack APIs. So here's an example of how our users would declare that this specific target's actions can access the browser stack domains. Pretty straightforward stuff here. For each Basil action that requests internet access, we spin up a TCP listener inside the micro VM that acts like a simple SOCAT, the blue box here. The SOCAT just shoves bytes into this VSOC, a mechanism for network communication between a VM and the host kernel. On the output end of the VSOC, we connect a dedicated instance of the smokescreen library, an open source connect proxy. This orange box here. This per action smokescreen then proxies over to this other instance of smokescreen at the VPC level, which in turn proxies to the internet. So it's proxies all the way down. So this SOCAT-esque TCP listener here is exposed to the action environment itself through the HTTP proxy environment variable. This is a standard environment variable. All HTTP clients kind of know how to use it. And that just makes actions work out of the box that want the internet. But only those domains, right? So at this point, you might be asking yourself, why is Sushain making such a big deal about security and then allowing any action to just talk to the internet, right? I could tell you that CI jobs that run tests, that only run tests can access the internet. But that really shouldn't satisfy you, right? Wouldn't the remote cache that we talked about allow other jobs to access these internet poisoned actions? So that's where cache tags end up coming in. So to make that more concrete, the orange CI job here should have access and should be allowed to read this cached remote cache entry that accesses the internet. But the green job shouldn't, because it ends up producing some binaries that we end up deploying to production, right? Unfortunately, a naive remote cache would permit both of these things to access this cache entry. So here's where tags end up coming into play. So rather than being indexed by action digest, like we saw earlier, mapped from action digest to result, our action cache is indexed by action digest and then a set of tags. So this network tag here denotes an action that required network access. Kind of straightforward there. When fetching actions from result cache, Basil clients can specify a set of tags that they're willing to read in a header. And a remote cache service filters the existing cache results with a subset operation. So by injecting a tag without the network header, our green CI job is prevented from reading this poison cache entry we talked about, poison, I guess. And the orange one can, since it has that network tag. So we've got more than just network, right? Our insecure tag denotes an action that was built locally rather than remotely. So it can't be trusted in any sensitive situations. In the future, we plan to use tags like containerd to denote actions that were built with containerd. It's kind of like Docker. Containerd is a less secure sandbox, which could offer performance improvements for tests and a little bit cheaper. So at the end of the day, we're much less worried if tests do something kind of wonky, and the worst case is an attacker modifies whether test passed or not. Not a big deal. So the tags just aren't namespaces. That's not quite what they are. A single action can have multiple tags, right? By default, we tag our actions with the environment that they're built in, like QA or prod. Our QA users often send QA comma prod so they can access action results and cache results from both QA and prod. A prod reader that sends containerd and network, for example, can access results that were built with containerd or use network access, or both of those two things. So let's switch gears to reliability. We've got some pretty fun tricks up our sleeve here. So you read that right, time traveling. Okay. On the 1st of January 2020, this test started failing, along with like dozens more just like it. We call tests like this one time bombs, since they go boom whenever the calendar ticks to a specific date. Plenty of tests fail at UTC midnight, the day they're introduced, and I've even seen tests that fail only on leap days. Yeah. We used to take bets on how many of these would fail every New Year's. And that was really fun for our skip. It was a lot less fun for us when we got paged on New Year's. Users were pretty happy. They just couldn't merge their PRs, right? Fortunately, Basil remote execution provided us an opportunity for a highly leveraged solution to this problem. So with a single exec property inside the platform used for remote execution, container clock time, Basil clients can convey a desired starting clock time for actions. Here, you can see we're traveling to August of 2029. Since our sandbox is powered by micro VMs, we could translate that exec property into a call to the set time of day syscall within our init process. This one weird trick, it eliminated time bombs once and for all for us. So Basil's remote downloader is another one of our core reliability mechanisms that we have. So you might be familiar with the experimental downloader config flag. It tells the Basil client to rewrite URLs before making an HTTP request. So we don't quite use that. Instead, we use the experimental remote downloader flag, pointing to a gRPC implementation of the remote asset API. This gives us a lot of leverage, we'll talk about it in a bit, especially in combination with this very, very succinctly named flag, experimental repository cache URLs as default canonical ID. Okay, got that out. One breath. Okay, the remote asset API, it works by having the Basil client issue a fetch blob RPC, step one here, with the URL that it wants to download. Then the downloader service goes and pulls that blob from somewhere, for example, from Artifactory, and it writes to the CAS. That's step two. And then it returns the size and the checksum. If the blob if the blob's already present in the CAS, it skips the write. So then that allows the Basil client to read that from the remote CAS with 3. So this API, it isn't too fancy, right? But it gives us just the knobs we need for reliability. For example, we can force that all our downloaded blobs have a checksum in the source to ensure deterministic downloads. With the canonical ID flag, we also get to ensure that the checksums match the URLs even better. We're also resilient to upstream downtime. You might remember earlier this year when GitHub.com changed its Git archive checksums. Since our downloader is backed by a caching proxy like Artifactory, we didn't even notice this problem. Finally, we hide the actual artifact sources from our users. This is proxy things like S3 objects and transparently change our backends. No one notices. And so finally, what you've all been waiting for, performance. Let's dive into some of our system's features intended just for performance. We'll kick off with one of the user-facing features, integrated tracing. You might be familiar with Basil traces, but you can create them with the -- profile JSON flag and open them up in something like the Perfetto UI. You might also be familiar with distributed tracing. We support both of these for our builds, but none of them cover the bits of execution our users are most interested in, the action itself. It's just one big opaque span in this honeycomb UI here. So that's where the first part of our integrated tracing support comes in. Using the stripe/tracing exec property, users can specify an HTTP address and/or a gRPC address. Then we automatically spin up servers at those addresses that accept Chrome trace event JSON. That's the same format that Basil traces use. Here's a minimal trace that our JS infra team added to their Webpack builds. They are actively using traces like this to debug performance issues. Now, our execution service exfils these traces without interfering with the action's actual outputs. Right? If the traces were action outputs, on the other hand, actions would become super non-deterministic because these traces have things like timestamps in them. And that would totally wreck our cache hits. So that's not all the stripe/tracing property supports. Google's Perfetto system isn't just useful for making those pretty traces, right? It also provides a toolkit for system-wide tracing and profiling that plugs directly into the Linux kernel. So we support transparently kicking off Perfetto within an action and configure it together perf events, process stats, ftrace events, and system stats. Each of these 4 modes is configurable straight in the exec properties for our users, as you can kind of see here. And I have various little knobs to enable and disable little features. So here's an example trace from one of those 4 modes, ftrace. This trace is from a JavaScript test action. There's 8 cores for its micro VM. And you can see the details what every core is up to, like Lots of fun colors there. On the other hand, like the process struts mode thing I mentioned, it includes memory, I/O, and CPU usage for each process within the action. I'd say that even just this ftrace thing here gives you like 4 orders of magnitude more information than we were seeing earlier with one single blob, just nothing in there. So our users are currently enabling these on an ad hoc basis when they kind of want to figure out something about some action that they doesn't quite behaving right. In the future, we hope to support them just enabling it straight all the time and providing some kind of sampling configuration. And then we can sample that out and we can spot regressions over time. Traces can be pretty expensive. So switching to something that's more behind the scenes. Action merging is one of our simplest yet most effective strategies. Basically, if someone's already asked for an action to be executed, just wait for them to do it instead of doing it yourself. Sounds pretty simple, right? Here's an exaggerated example just to show you what it looks like. We've got 2 sequential commits to the main branch that edit 2 unrelated projects, commit A and commit B. Say commit A edits a project with a single action that takes 20 minutes long, like a long integration test or something. Now commit B's build, it's got to run that too, since it only ran 5 minutes later. It's not cached yet. Kind of sad. So we can do better than this. With action merging, commit B's execute RPC blocks on commit A's RPC, reusing its result and resulting in both builds completing simultaneously at that 10:50 a.m. point. So commit builds B's build is now 25% faster. So there's a lot going on here, but our action merging implementation is actually pretty simple. It's powered by optimistic locking in Dynamo and some polling on top of that. Here, execution A started first, and it took an exclusive lock after 15 seconds of executing. Then it refreshes its lock every 15 seconds afterwards until it's done at 2 minutes 15 seconds. On the other side, execution B, it found a lock because execution A was already well underway. It started waiting on it and checked the lock every 5 seconds, and it didn't expire, and it got it back at 1 minute 45. It also was able to reuse those results from DynamoDB. So if the initial check didn't reveal an existing lock, or that lock expired at any point, execution B would have just given up on waiting and done the work itself. So action merging is a big performance win for our users. It's obvious enough for end users to notice just by looking at build durations. It's also a huge efficiency win, reducing our load on our executors by 20%. But it's not quite perfect. If a flaky test happens to be merged across 5 builds, you suddenly have the impact magnified 5x of that one flaky test. We've also seen other correlated failures, like flaky resource suggestion on build targets. So we're exploring some hedging strategies to kind of mitigate that a little bit. So one idea is like if 8 clients tell us to do the same thing, we'll execute it 4 of those times and then pick the best one of those 4 times. So we've also identified that our implementation leaves some efficiency and some performance on the table. In our Java Scala Python monorepo, up to 15% of actions are unnecessarily repeated, and we look at them afterwards. So we're thinking of moving action merging into our scheduler rather than our executors, and that would allow us to hopefully eliminate that waste and implement some of the more fancy hedging strategies that I just mentioned. So the next strategies we'll discuss are motivated by actions with a lot of inputs, and you might know what's coming here. It's like a black hole filled with node modules directories, right? So huge swaths of our actions have input roots with over 500,000 files. Right? Getting these files into a micro VM is a lot easier said than done. Sort of one way of doing it. We'll talk about another one. LVM snapshots are our first line of defense here. So let's first go the traditional way. So like sandboxing with like Docker. So first thing, your build worker goes and downloads a bunch of blobs into this thing called the blob cache, and they're named based on their checksum, kind of similar to how Basil's remote cache is laid out. Then your worker creates an input route with hard links. We'll call it a hard link forest. For example, a file here called foo, just a hard link back to the file here with its content. Finally, create a bind mount to make it so that the hard link forest is visible within the action sandbox. Unfortunately for us, bind mounts aren't quite possible with Firecracker and KVM virtualization in general. Because the guest and the host don't share a kernel, they're completely disconnected. So this is super fast. We still want something fast, though. So we settled on LVM snapshots. LVM stands for Linux Volume Manager. It's kind of like a partition manager, but a lot fancier and built into the host kernel. So the first 2 steps here are unchanged. But instead of bind mounting, we use LVM APIs to create a copy on write snapshot of this hard link forest. The snapshot's block device is then attached to the running VM, Firecracker VM. It's kind of like how you might stick a USB port into your a flash drive into your PC's USB port. So this lets us transfer gigs of data across hundreds of thousands of files, just a couple hundred milliseconds, without using any extra disk space. We can evenly transparently GC blobs here because the action at the end of the day is using a snapshot, right? So this strategy isn't perfect for everyone. We're exploring some alternative solutions. For example, non-sensitive actions could just execute with containerd and use the bind mounts that we talked about. We could also use fancier file systems like nilfs that allow snapshotting built into them, and NFS network file systems and things like that. Especially for actions with fewer inputs, that could be particularly helpful. So let's step away from fancy Linux features for a second. Let's talk about our tree cache. So we'll kick this off by talking about the remote execution protocol's more esoteric RPCs, the get tree RPC. So the get tree RPC takes a root directory as its primary input. Then it returns a stream of leaf directories by recursively walking the given root directory. As far as I know, the Basil client does not actually use this RPC, but it's pretty critical for a remote execution worker. Our implementation uses it to unfurl a action input root so that it can create a file system for the action to run inside of. So unfortunately, serving this get tree request is pretty tough for large directories. Our naive implementation took over 10 seconds for single root RPC for like large Ruby vendor directories, pretty similar to node modules, but for Ruby. So here's an example of a tree on the left where a single file, badge.tsx, changed since the previous actions execution. Every other branch in the tree hasn't changed. The list of flattened directories in each one could be safely used. So that's what we did. Directories that aren't too deep in the tree are cached in DynamoDB as a map from that directory's digest to a digest of the flattened tree, and those flattened trees are stored in the cache. This dramatically reduced the cache fetches we needed to respond to a large get tree RPC. But, this wasn't quite enough to fix it. We also switched to walking this tree serially to walking each level of the tree in parallel with a worker queue. Each worker either fetches the unfurled tree from the cache, the tree cache, or recursively descends. With both these optimizations in place, we saw a 20x improvement in get tree latency, hovering around 500 milliseconds at the end of the day for large trees. So the final stop of our random walk is another fun Linux feature, SquashFS. SquashFS is a read-only Linux file system. Imagine if you could just mount a compressed tarball and arbitrary processes could read directly from that. So we found that large trees like node modules continue to pose performance challenges, even with that LVM snapshot thing we just mentioned. Building these Merkle trees inside the Basil server and checking for missing files in the cache for every single action were both expensive operations that just didn't scale well for us. So our solution was adding Basil targets that create SquashFS images of directories that don't change frequently. Here's a partial MK SquashFS readout for a node modules directory. It shows that we went from 108,000 files in here to a single file, and the compression eliminated almost a full gig of disk space. So targets are responsible for telling us how the SquashFS files that they want should be mounted. They're specified through an exec property, either directly or indirectly. Indirectly is required when the set of mounts isn't known at loading phase. The exec property looks a little bit generic, but really we only support SquashFS mounts. After parsing a list of mounts, there's just a couple steps left for each SquashFS. First, we do some Linux shenanigans to get a loop device and bind the SquashFS to it. And we create some temporary directories, the blue things here. We mount the SquashFS, the lower directory, and then create an overlayFS at the destination with these three directories. OverlayFS is just another Linux file system that basically allows for unioning multiple file systems. It's how container image layers are usually wired together. The overlayFS mounts allow Basil actions to write to these directories, even though SquashFS is a read-only file system. So you get writes even when you would otherwise. So with our node modules example, the node runtime never even notices just running files from a SquashFS, and everything just works transparently. To our surprise, some of our largest actions actually experience a 10% speed up relative to running natively completely outside of Basil. We think this is due to SquashFS providing improved I/O locality. For small files smaller than 4K, a file system block, SquashFS is actually going to compress those together for you. In our JS builds, we also saw a 50% drop in memory usage, which we're all happy about. This was entirely attributable to smaller Merkle trees. Finally, the hard link force that we talked about can require an order of magnitude fewer hard links, a lot fewer syscalls. So we've talked about security, reliability, and performance. There's always trade-offs when it comes to these goals. But we've worked really hard to get the best of all the worlds in our builds. it's safe to say that Basil doesn't always cater perfectly to the workloads that our users are interested in. Fortunately, the flexibility of the remote execution protocol allows us to build custom features into our services that really push the envelope of what's possible. By working closely with our users, in particular all of our Stripe's language teams, we're able to focus on building what's most impactful. We found time and again that like these power user features we built are quickly adopted by other teams as well to improve their builds. Thanks for listening. I hope you're inspired by something that we've tried out. I also wanted to give a quick shout out to all the individuals and teams at Stripe that have contributed to our remote build services. We've had major contributions from our JS infra team, our Ruby infra team, and our security teams over the years. I'm just here talking about all their great work. Any questions?
I would just speak it. Hey, oh, Matt. All right. Hi, I just want to ask in detail about the cache tagging. You said those were sent to the remote server using a spatial header. How do you define that headers in your build for specific actions?
So it's not per action, it's per invocation, because the security model is basically that if you end up having a pipeline or a job read something insecure, it's basically poison for the rest of its life, right? So that's a gRPC header. The format is just a proto that's a string of tags, basically. If you don't provide that header, you default to just like your environment. So you can read things that are built with your environment securely without network access, without any shenaniganry. That's what you get to read. But if you get to specify more, then you get to read more interesting things that might break some invariants that we like.
Can I ask a question? This is pretty amazing stuff. How long did it take you to build all this, and how big is the team?
I think that our team is about 10 people, but a lot of this stuff has been built up over the years. I wouldn't say it was built up in any like specific big master plan, right? It isn't that bad. Yeah.
I have a question over here about the overhead of gvisor. Do you think that the overhead you see with gvisor is specific to that implementation, or would you see a similar kind of overhead with any mechanism that involves like say like NFS or Fuse or anything where you're like virtualizing file system access?
So I don't know. We haven't tested this yet. But the problem with gvisor in particular is that it's user space file system implementation. That's similar to Fuse. But there's also a process jump between things. And gvisor actually released a different version of their file system, GFEX v2 or something. Just wasn't good enough still. And yeah, we'd have to try NFS. We'd have to figure that out. We're curious, but thanks.
Hi there. Oh yeah, this, here on the in the center. Yeah, that's where I am. So I was wondering, with all those optimizations you have in place, what's sort of like the ratio of time being spent on input root population versus actually executing the action? What's the overhead?
It's a good question. So for actions that run a longer time, we don't really mind as much, right? But we have a lot of actions that want to run like for say 10 or 15 seconds, right? And if we spend 10 seconds populating input root, they're gonna be like, why am I using this Basil thing? It's trash, right? And so we wanted to get those actions to be able to talk. We're talking like low single-digit seconds at the upper end for those.
I had a question about the tracing. So we are showing the sort of within action tooling specific tracing. I'm wondering, how is this done? Is this like tooling specific instrumentation, or how does that work?
So the system traces I mentioned, they're from Perfetto, right? We don't have to, we just let Perfetto write the files, and then the Perfetto UI can then process the protobuf that those write. For the application specific ones, yeah, the action under load has to be able to produce these traces and push them to us. But a lot of folks are already integrating Chrome events trace style. So all we have to do is, instead of write to a disk, just push to the server, done.
Over here. All of this sounds pretty nice. Where can I see any of it?
Yeah, I think it's you can come to Stripe. You work with us. But yeah, I think we're totally open to people trying to implement the same stuff. We're happy to help. I don't know if we're necessarily thinking about open sourcing any of it. At the end of the day, a lot of this stuff is not super complicated to kind of sure Buddy could implement it in like, I don't know, a month or something. So hopefully they're inspired.
I guess the follow on to that is that it seems like you've done some interesting things that allow your clients to control things like the tracing APIs, and the SquashFS identification. That seems like it might be something publishable as a standard. Is there anyone working or that we can reach out to sort of seek the ability to publish a set of standards for, instrumenting remote execution in that way?
I think that sounds really interesting. I mean, we'd be happy to chat about it. I think that either tracing is one and mounts and remote actions would both be really interesting. I've heard a little bit about remote execution v3. Maybe that's something we could toss in there. Pretty cool.
All right, thank you for saying.